Welcome to The Explainer. Today, we're going to dig into a new theory that tries to solve one of the biggest puzzles in all of cosmology. A puzzle that's only gotten deeper thanks to some incredible new observations from the James Webb Space Telescope. So, you may have heard about this cosmic mystery that has scientists buzzing. The problem itself is pretty easy to wrap your head around, but solving it? That's a whole other story. Supermassive black holes just seem to pop up in the early universe, already enormous, way faster than our current theories say they should be able to grow. And these new observations have kicked off a ton of headlines and some really exciting new scientific ideas. But, as it often goes, the actual research papers are way more specific and frankly more cautious than the news coverage might lead you to believe. That's what we're here to do today. We're going to look directly at a new theoretical paper that offers a pretty radical solution to this cosmic puzzle. We're going to break down what the authors are proposing, what they're not proposing, and why it's such a fascinating new piece of this whole puzzle. Okay, so here's the plan. We'll start by getting a handle on just how big this problem is for astronomers. Then we'll look at the fundamental physics that makes it so tricky. And finally, we'll explore the brand new solution this paper is putting on the table. So this paper we're looking at from physicists Pierre Sikivie and Yuxin Zhao jumps right into what they themselves call an enduring mystery in astrophysics. And really, this whole mystery boils down to one thing: timing. We see these absolute behemoths, some weighing up to 10 billion times the mass of our own sun, already fully formed when the universe was just a baby. Our standard models of physics just don't have a way to build something that big, that fast. Okay, so here's the really interesting part. The main thing stopping these black holes from forming isn't some weird, exotic new physics. It's actually a fundamental law of the universe that you see in action all the time. It's called the conservation of angular momentum. Just think about a spinning ice skater. When they pull their arms in, they spin way faster, right? That's because that spin, that angular momentum, has to be conserved. It has to go somewhere. Now imagine that ice skater is a giant cloud of cosmic gas. For it to collapse into a black hole, it has to shrink by a mind-boggling amount. And as it shrinks, just like the ice skater, it would spin faster and faster and faster. Eventually, that spin creates a powerful outward force, a rotational barrier, that just stops the collapse in its tracks. And getting rid of all that spin is, in conventional physics, a really, really slow process. And this is where the new paper comes in with a really fresh idea. The authors suggest, hey, maybe we're looking in the wrong place. Maybe the answer isn't in ordinary matter at all. Maybe the answer is hidden in the nature of dark matter itself. The theory goes like this. What if dark matter is made of these hypothetical particles called axions? Well, if that's the case, they can do something really strange. They can form what's called a Bose-Einstein condensate, which is a fancy way of saying millions of these particles start acting in perfect unison, almost like a single giant particle. And that weird collective behavior turns out to be super useful for our spin problem. So here is the absolute key takeaway. This axion condensate develops a kind of, think of it as a long-range viscosity, a stickiness that works over huge distances. And what it does is it basically grabs the spin from the center of the dark matter cloud and flings it outward. With that spin gone, there's nothing left to stop the core from collapsing, and it can do so directly and very, very quickly. It's a neat way to just sidestep that whole angular momentum problem. So what does this mean for the big picture? Well, if this is right, it basically rewrites the timeline of how the first big structures in the universe even got started. It's a fundamental change to the standard story we've been telling for decades. See, the conventional view is that a galaxy forms first, and then over billions of years, a supermassive black hole slowly grows at its center. This theory flips that picture completely on its head. And the authors say it best themselves. The supermassive black hole isn't a consequence of the galaxy, it's the cause. The black hole forms first, all on its own, and then it acts as a massive gravitational seed around which the galaxy we see today later gathers. Now, this next part is really important. The authors are incredibly precise about the physics they're describing, and they even include a whole section in their paper just to address common questions. This is key to understanding what the study does, and, just as importantly, what it does not show. The first, and maybe most important clarification, is about the kind of physics we're talking about here. This isn't something you can just model with the usual simplified equations that are often used. In short, this is a deeply quantum phenomenon. The authors make it crystal clear that if you use the simpler, more common equations to model this situation, it just plain doesn't work. You would not get a black hole. This special property that lets the spin get carried away only shows up when you use the full, more complex quantum description of the system.
Okay, another common idea you hear about in axion physics is the formation of a stable object called a Bose star. The authors are very quick to say, nope, that is not what's happening here.
And the difference is actually pretty simple. A Bose star is stable. It's an object where gravity pulling in is perfectly balanced by a kind of quantum pressure pushing out. The process this paper describes is a dynamic runaway collapse. It's all one way. There's nothing pushing back to stop gravity. And that's exactly why it can form a black hole directly. So after all those very specific, very technical details, you might be asking yourself, all right, so what? Why does this matter? Why is this idea so interesting to scientists? Well, the real elegance of this idea is how clean it is. It gives us a natural way to form these 10 billion solar mass monsters right at the dawn of time. You don't need complicated, multi-step processes or a bunch of extra assumptions. It suggests they can just form directly and be huge from day one. So looking just at the paper itself, what can we responsibly say? We can say that this is a fascinating and really elegant new proposal. It's a clever idea that connects two of the biggest mysteries in all of physics, the nature of dark matter and the origin of supermassive black holes. It's definitely not proven, but it is a compelling new idea, and it leaves us with a truly provocative thought. You know, for decades, we've studied galaxies to try and understand the black holes at their centers. But maybe we've had it all backwards. Perhaps to understand how these great cosmic cities of stars are born, we first need to understand the strange quantum world of the dark matter that built their foundations.